All right, welcome back, everybody. So next up, we have Elena Provornikova, who is our heliophysics science working group lead. And she's going to talk to you about the trade between the direction we go in and the science that we get out of it. From the very beginning of this study, people asked, where are you going and why? And working out the answers to that has involved not just Elena and her own insights, but a large group of people who have weighed in on what makes sense. And with that, Elena, the floor is yours.
Thank you very much, Michael. And I just wanted to add that, when people say, okay, where are you going? And here's the exciting science we can do in this particular direction. So we got a lot of input from community about different directions. Okay. I'm waiting for my slides to share.
I think Kirby was going to drive this deck of slides. I can do so if he's not available at the moment.
I can bring it up as well, Michael. Just give me 1 second. Oh, there we go.
Okay, here it is.
There. Thanks, Kirby.
All right, thank you. And let's go to the next slide. All right, so here is the plot that you saw already in different presentations. So as we heard from previous presentations from Ralph and Pontus and Jim, our approach is to present a menu of directions for the interstellar probe. Where could the spacecraft go and what science we can achieve in different trajectories. So this is the map of the speed for passive Jupiter gravity assist, and it shows hot zones where we can achieve high speeds and between 7 and 8 astronomical units per year, and zones with low speed. And this calculation includes the rocket configuration, the SLS Block 2 plus Atlas 5 Centaur and plus Star 48 BV, and also depends on the mass of the spacecraft. Here we assume 860 kilograms. No, go back. So let's orient ourselves a little bit in this map. So to point you to the nose direction of the heliosphere, so this is around 250 degrees in longitude. You can see it's marked by the blue nose. You can see the nose direction. So, and also the tail direction would be around 70 degrees in longitude. So the first opportunity to go to the forward hemisphere, where the nose is, sort of around there, this is the option A, which opens in 2036. And so this is 80 degrees from the nose and 20 degrees below the ecliptic. This direction sits at the edge of the ribbon, the ENA ribbon that IBEX observed. And on this plot, you can see the contours. They're barely seen, but you can still see them, contours that outline the ribbon shape on this map. And so this option A was used to design the mission architecture. And the option A is followed by other opportunities that open up every 13 months to maximize the speed of the spacecraft, which also provide the speed between 7 and 8 astronomical units per year. So option B would be to launch in 2037 and is roughly 50 degrees from the nose, and option C is about 50 degrees also from the nose to the other side, so both in ecliptic plane. So now let's go to the next slide and look at the different directions that we discussed during the mission study over the last several years. So community gave us a lot of input to lay out the scientific advantages of these different options. And I'm summarizing these options on this and next slide. So the nose direction, if we go to the nose of the heliosphere, this would provide us the fastest way to get to the very local interstellar medium. It also gives us opportunity to study in situ the stagnation region in the heliosphere and the high pressure region in the heliosheath, and also the in situ studies of regions where energetic neutral atoms created that form ENA ribbon and belt. And you see on the right here the map of the ENA map in energy 1.74 keVs. You see the Voyager 1 direction, Voyager 2 direction. So those two they did not intersect with the ribbon. And you see the marked the interstellar probe direction on this ENA map. And so here on the right map, you see this is the map from Cassini Inca ENAs. And here you see the ENA belt, and also with interstellar probe direction marked, not right at the nose, but close to the nose. And also the nose direction would be best for interstellar probe dust investigations. However, it may not be optimal for imaging the shape of the heliosphere once interstellar probe is outside, because if you go right through the nose and then you look back at the heliosphere, it may be hard to distinguish the global shape if you're looking right through the nose. So the next option is going 45 degrees of the nose. So this direction provides the direction through the ENA ribbon, and would be sufficient for imaging the heliosphere from outside in ENAs. And Bob DiMagistri led the simulations that show that you can actually distinguish between different shapes once you are outside the heliosphere in this direction. And this direction would also be good for measurements of interstellar dust. Now the next direction, we go further from the nose toward the flank, 90 degrees of the nose. This is one of the interesting directions to go. So this would provide the new data point for the heliopause location, and this would be important for understanding the global shape, because some simulations show that, of course, as you go further from the heliospheric nose, the heliopause, the distance from the sun to the heliopause would increase. So the heliopause stands further out from the sun in the flank than in the nose. But there are other theories that suggest that heliopause is more like, resemble more like a bubble around the sun. That means that maybe the distance to the heliopause would be close to what Voyager's measured in the nose. Also, the flank direction would be interesting for the acceleration of the anomalous cosmic rays. There is this idea that anomalous cosmic rays are accelerated not necessarily in the part of the hemisphere around the nose of the heliosphere, but rather at the flanks of the termination shock. And here I'm showing this picture from Akomas and Schwader in 2006. If we go to the flank, 90 degrees of the nose, it may be possible that we would be able to directly sample the acceleration mechanisms for the anomalous cosmic rays. Also, this direction, it may be longer to reach the pristine interstellar medium if we go to the flank. This is not in the ENA ribbon, not through the ENA ribbon. And also the dust, the duty cycle would be limited in this direction. Okay, now if we go even further from the nose, 135 degrees of the nose. So this direction would be problematic for the dust, interstellar dust studies. But this direction is pretty interesting, because this is the direction which is sufficiently close to the direction toward the star, Epsilon CMA, which is, it's pretty far away. It's 124 parsecs away from the sun. But this star is the brightest source of extreme UV radiation in the local interstellar medium, and it produces a large photoionized region around those four interstellar clouds that are in contact with the heliosphere. And so this direction is interesting because it particularly opens opportunities to study effects of increased radiation as we go further away from the sun and ionization of the very local interstellar medium. All these options, perhaps except the last one, would provide directions of the spacecraft going through the hydrogen wall. And this is something we discussed yesterday. So the hydrogen wall is the pileup of interstellar hydrogen around the heliosphere. So as we go toward the forward hemisphere, we would cross the hydrogen wall and make in situ and both remote measurements of this interesting structure around the heliosphere. And next slide, please. So there are two more interesting directions, maybe more exotic directions that we also considered in previous workshops and discussed. So the first direction is going to the tail. And it's interesting because the tail is completely complete mystery for our heliosphere. The structure and extent of the heliospheric tail is one of the biggest open questions. So here on the right, you see different theoretical predictions how heliosphere might look like in the tail direction. Some models predict that the tail would be filled with the solar wind past the termination shock. So this is the shocked solar wind, slowed down and heated. Another model from BU group offered all 2020 shows that heliosphere looks more like a croissant, meaning that in the tail you would have a boundary between the solar wind and interstellar material. And there is another model from Zheng et al. 2020 showing that the heliosphere tail would may extend down to 6,000 astronomical units to the tail. So there is exciting physics of the tail region of the heliosphere. However, if we go to the tail, we may not ever reach the pristine interstellar medium. So this direction also may not be good for dust measurements, not through the ENA ribbon, not through the hydrogen wall, and also it's sufficiently close to the direction toward Epsilon CMA star, which is, as I said, a major source of radiation in the very local interstellar medium. And another exotic direction is going off ecliptic. Yesterday, Mirav showed recent simulations from BU group that show that the heliosphere may form those large turbulent structures as you see on this plot. And if we could go with sufficient speed through those turbulent structures, it would be a great opportunity to look at the particle response to these structures and particle acceleration processes. And I think I'll conclude here my presentation. If you have any questions or comments, please put them in Q&A.
All righty. Thank you, Elena. Thank you very much. So we have a couple of questions already. John Cooper is asking if the project can provide detailed trajectory listing in solar ecliptic coordinates for the 3 different options. Would this be useful for studying, he says, possible closest approaches to untargeted solar system objects? Yes, we are going to look into that. We have, of course, the baseline trajectory is the way that we're publishing it. It'll be option A, and you can glean those coordinates off of a plot like this, but we're going to look into publishing the trajectory details alongside the report on our website when the time comes. We definitely don't have anything to hide there. We just want to make sure that we do it properly so that it's understandable information from everybody who wants to download it and per the process. We expect an abundance of objects no matter what direction we go in, but learning from all of you where the interesting places to go is certainly certainly something we want to hear. And Kirby Runyon has talked a lot about that past. So stay tuned for more of that, and we'll definitely make sure that such things are available. The next question, Elena, comes from Michi. He says, how different would the instruments need to be for the different directions?
This is a good question. Thank you, Michi. So I think I can start, and then maybe Alice can help me to extend. So if we talk about in situ instruments, then I don't think there would be dramatic changes in instruments as we go to different directions, because you just making in situ measurements along this trajectory, and each trajectory is new. In terms of we've never sampled heliosphere in these directions. We only sampled in situ in Voyager 1 and Voyager 2 directions. For the instruments that do imaging, I think depending on the trajectory, we might be able to adjust field of view, right? To make sure that we cover, with the imaging, we cover the interesting parts of the heliosphere. So as we change the direction of the spacecraft, there may be adjustments to the field of view. But I would let Alice comment if she has anything to add.
That's a great answer, Elena. I would say that in general, nothing about the instrument itself would necessarily change, but the accommodation might need to. So for the particles in the fields, those all have almost 4 pi steradian coverage already. So those would be fine. For the ENA and Lyman alpha, the neutral mass spec, and the interstellar dust analyzer, the ENA imager just needs a sun exclusion zone, and that's going to be taken care of no matter which direction we fly out, because the sun will always be behind us. So that wouldn't be different, because it also almost has full sky coverage. But for Lyman alpha, NMS, and IDA, which all are trying to look at the noseward direction of the hemisphere, more or less, there would need to be some changes in accommodation in order to make sure they could point the direction they need to point. But no, in my opinion, probably no changes to the instrument itself.
And actually, Jamie Zalay talked a little bit about that yesterday in terms of the field of view for the dust detector needing to shift depending on what angle we're at with respect to the ram direction. And as you said, Alice, it doesn't change the instrument itself, just what direction it's mounted on. So, all righty. We did get a question from Niben about presentations. This is a general question. All the materials that are presented, you'll find at the agenda on our website. For each of the presentations, there's a plus sign next to the presenter's name. You click that and it expands a view that shows you the slides. It'll also show you the recording of this talk and all the other talks as they get uploaded to the website. So you can always go back and find more there. So let's see. Do we have any other questions for Elena at this point about the direction we go in, the trades that went into it, and where the program is thinking to send this for now? Keeping in mind that we know as a study team, the directions that we've studied and looked at are not necessarily the ones that a science definition team or a future mission will follow. But we've done a lot of work to try to make sure that what we show here as a pragmatic and feasible mission can go in a lot of different directions and still be a very worthwhile mission. And Elena's description of the different discussions around the angles with respect to the nose was our effort to make sure that no matter what direction this goes in programmatically or trajectory-wise, it's a good one for science. So.
And I just want to, again, thank the community for a lot of input that went into this trade study. That was fantastic. Thank you.
You're muted.
Thank you, Pontus. I was muted. We've got a new question here from Niben. A recent study from CNRS, which I'm not sure what that is, has found that the galactic winds aid in the transfer of normal matter to the nearby galaxy from one to the other. Does Interstellar Probe have an eye on recording this event?
Well, Niben, thank you for your question. I'll take a task for myself to study this recent study, and maybe I can get back to you on this.
If there's a reference, that would be very helpful. And I think you may be referring to also the somewhat controversial speculations in dust winds from other galaxies, from galactic directions, but I'm not sure.
All right. So thank you very much, Elena. We have now hit 10:50.